is a current loop, right? So there's a current, which is this red is usually there's a power supply here, which are going to go through these many round winding of current loop. And this is the positive, and the red is positive, the black is negative, or relatively one is more negative, more positive than the other. Okay, so which way is I guess you can't see it, but it's wounded so that it's going like this. So which way is the magnetic field pointing? Out. Okay? Okay, so we can test that. So I turn on this power supply, which is, this is just, don't get excited, I did not get electrocuted. Okay, so I turn on the power supply, which doesn't turn on. Plug in.
Yeah.
Plug in.
You're Mindy.
Okay.
Hold on. This one here.
I can put my idea.
Pick up.
Still not on? Let's see.
What's my goofy? Huh?
This is what?
Irish.
Oh, Irish.
Oh, it's on. Okay. Because the circuit breaker was tripped. All right. Oh, so now there's a voltage, and there's going to be a current, and the current is actually 3.4 amps of current, and the voltage is about 12 volts. 6 volts. Sorry, 6 volts. Okay, 6 volts, 12 amps. Then you can calculate the resistance, right? Okay. So the magnetic field points out this way. So this is the north. This is the south. Magnetic field points this way. Okay, if I go like this, in the middle. Okay, so it's, you can see the red is the compass. I mean, this is basically the compass. It's the North Pole. So it's pointing along what direction? Is it along the magnetic field or against the magnetic field? Along the magnetic field, right? You can see? And then if I rotate this around, okay, so which way is the magnetic field now? Imagine this is horizontal. Let me see. Better. So along the side, it's pointing what? Into this way, right? Okay, which makes sense. And then if I go around this in the back, you see it's pointing towards the center now, right? Right? So it's pointing this way. So this is compass, which points along the magnetic field. Do you believe me? Okay. All right, you can see, try again. You see here? Pointing out?
Yes.
Goes around. And then comes back.
That's just a magnet. You see?
You see? Okay. So in the back, it's actually pointing this way, right? Magnetic field. On the here, it's pointing out, right? So it's pointing this way, and then you have a south pole and a north pole. Okay. South pole on the back, and north pole on the front. Okay. So that's that one. Okay. Now I'm going to connect this this thing here to the same power supply, which is going to connect pass the current through this loop. so let me turn this off. Pass the current. So here is the positive terminal of the battery. Go through this strip, aluminum foil, which is metal, and then goes back to the power supply. So very simple circuit. Battery puts out current, goes to positive, goes through this way, through the foil, and then goes back. Okay, so the current goes from left to right. Okay? And they have the north pole, south pole on this side. So which way is the magnetic field pointing? So north, south. North in front, south in back. So the field always comes out from the north pole, emanate from the north pole. Goes around, and then goes through the magnet, south pole to north pole. Okay, so the magnetic field in between the north and south is pointing this way. The current's going this way. Magnetic field this way, current going this way. Which way is the force? Down. Let's see. If it points up, then what will be the point down? It will not be a good demonstration because it cannot go down. So it has to go up. Let me see. Hmm? Goes up. Okay, so what does that tell you? So this magnet actually, the field goes around in the back and points in. Okay, it loops around. So the magnetic field points this way, the current goes that way, so the force goes up. Oh, you can see that too much current. I just start to, okay, let's do that again, huh? Maybe with less current. So the current is going from the left to the right, magnetic field going in, so the force goes up. Okay. Okay, watch. Okay. So you turn on the current, all created by the permanent magnet, and the force is up because the magnetic field goes from north, goes south, emanates from north and goes back to the south. So actually the field is going in. Okay, so the field goes in, and the current is going this way. The field goes in, so the force goes up. Okay. All right, so that's the second one. Hopefully you believe now there's a force for the current carrying. We use basically it's a current carrying wire, which is in this case is a strip. Okay, now this one here, along with this same type of experiment, we have here the two strips, and then we have positive here going through the strip, and then the current goes to the negative side, and then there's a switch here. There's a big switch. Okay, so the current goes up this way, and similarly for this one here, the current goes in here, goes up. So they are in the same direction, right? They're moving in the same direction. So what do you expect them to do? Attract? Repel? Nothing. Attract. Okay? That's what we determined in lecture. Okay, so you have a big battery. Yeah, this is not part of the circuit. Oh, so it puts out a lot of current, probably a 12 volt. Okay, so that's the, and then it's connected to a switch. So if I close the switch, we'll have current going up this tube in the same direction, and they should attract, right? Okay, let's see. Not very exciting. Let's see.
Is that trick tube? Oh, because it wasn't Chinese. It wasn't Chinese, so I tricked you.
Okay.
Huh.
I'll try that.
Okay.
Are you going
Sometimes it doesn't work.
But I can't authenticate it. So I don't think I
I
can
didn't know
do
what you
it.
meant.
Okay.
I don't even hear any sound. A little bit, huh? A little bit more flexibility. Should be a good connection. Not very exciting. Okay, this is, Okay, so this one here has a,
This one.
Well, we got it
this is
wrong.
what's called a Tesla coil,
Oh, we got it wrong.
which, if you get close, you see it has a very sharp point here. So when the sharp point, can establish a very high, voltage difference
The current's the same?
between this Tesla coil and this
between-
metal here,
Current between.
and then ionize the gas inside this tube. Okay, so there's going to be a current flowing in here. Okay, and so if there's a current flowing here, and if I take a magnet close to it, then the beam of the electron or the charge that's flowing here will be deflected. Okay, so we'll see whether that happens or not. And then you can tell me which way the when from the direction of the deflection and the magnetic field, then you can tell me which way is the current. Okay. All right. So this one here, switch is here. Okay. So there's the current, which is being affected by this magnet. Take it away. There's a current, right? Okay, so still deflected a little bit. Somehow there's some
What
very
is the ink there?
magnetic field. Okay, so I'm going to go like this. I'm going to put, let's say, north pointing this way. You see here? Okay, so north pointing that way, the beam is deflected up. There's a force going up, right? Okay, I have the north pole here. So the magnetic field is which direction? Going towards you. Okay, magnetic field is going towards you. The force is going up. Which way is the current? Which way? Is it to the right or the left? This way. Is it okay? The current is that way. Okay, the force is up. Right? And the magnetic field is out. The current is going that way for positive charge. Okay? So the positive charge, the current is going that way for a positive charge, up this way. So if I have a south pole pointing this way, right, which way is the magnetic field? Going out towards you. Magnetic field going out towards you, the force is up, the current is that way. It's okay? Alright, so that illustrates the I, L cross into B, right? I cross into B.